Hi, this video is aimed to introduce our latest work on INFOCOM2022, ONIONCODE, enabling multi-priority coding in LED-based optical camera communications. This report includes these 5 sections. Let's start with the background and motivation. Currently, radio frequency is widely used across various wireless communications. Even with efficient frequency and spatial reuse, the current RF spectrum is proving to be scarce to meet the ever-increasing traffic demand. In this sense, visible light communication, VLC, using the visible light band is emerging as an option to traditional RF communication methods and can be used to complement current RF systems. Compared with radio frequency, the visible light spectrum has unique advantages. The visible light band is not regulated and license-free, and is 10,000 times wider than the RF spectrum, meaning extremely rich spectrum resources. And the directional propagation of light allows VLC to effectively eliminate communication interference, creating data links of high quality. The widely deployed and energy-efficient LED can facilitate various applications of VLC, such as data sharing, indoor positioning, V2V and V2I communication, drone communication and underwater communication. Optical camera communication is a special form of visible light communication, using an image sensor array as the receiver and LEDs as the sender. The most attractive feature of OCC is the spatial MIMO or spatial multiplexing. Due to the structure of the lens and 2D image sensor in the optical camera, the receiver can spatially distinguish multiple LED sources while rejecting background pixels to achieve MIMO communication with high signal-to-noise ratio, and it avoids the complex MAC protocol design as in radio frequency. Therefore, OCC is well promising in densely deployed communication scenarios such as vehicle networks and UAV networks. However, in the one-to-many OCC communication scenario, distance becomes a major limitation on the system performance. For example, a V2I communication system uses the LEDs of a traffic light to send messages. A near receiver can spatially distinguish the individual LEDs, because the light spot formed by the two LED on the sensor array do not overlap. However, the LEDs observed by a remote receiver are spatially mixed, resulting in the interference between two LED channels and severe communication failure. If we ignore the channel interference described above, only the near receiver can communicate successfully, and the remote receiver cannot decode any messages. On the other hand, if we let the two LEDs blink synchronously to favor the remote receiver, the rate of the near receiver is forced to sacrifice. Therefore, our goal is to allow successful data receiving at the remote receiver, while do not sacrifice the data rate of the near receiver. The above limitation originates from the limited resolving power for point light sources of the optical imaging instruments, such as cameras and human eyes. This is physically described by Rayleigh criterion. Due to the Fraunhofer diffraction, the image formed by a point light source through a circular lens is not a geometric point, but a round spot termed as airy disk. If the distance between 2 point light sources is large enough, the corresponding 2 airy disks are spatially disjoint. If the 2 light sources is rather close, the 2 airy disks partially overlap and difficult to distinguish, which we call mixing. Between the disjoint and mixing, there is a critical state just enough to distinguish 2 airy disks, and this state is determined by Rayleigh's criterion. At this point, the radius of the airy disk is exactly equal to the distance between the centers of the 2 disks. To address the issue, hierarchical coding is proposed to support dynamic range of channel capacity in physical layer. That is, the LED transmitter encodes multi-priority bit streams at a fixed rate. Receivers at a shorter distance or a lower layer can clearly distinguish 4 LEDs, hence can retrieve more data and achieve a higher throughput. Receivers at a larger distance and suffering from spatial mixing, instead of losing all data, can still decode part of the information. Several previous studies have proposed hierarchical coding scheme to provide adaptive and scalable transmission capabilities for LED-based OCC systems, such as overlay coding and strata. However, the existing hierarchical coding schemes adopt a block-based coding. It means multiple LEDs or pixels in the same area build a block and blink together, which undoubtedly sacrifices performance of a near receiver, because the multiple LEDs or pixels within a block transmit the same information. Therefore, ONIONCODE is motivated to design a non-block-based coding scheme, where all LEDs blink independently to transmit different data and no longer sacrifices the data rate of near receivers. In ONIONCODE, all the LEDs on the transmitter encode the data independently in different priority. And the receiver discards one more bit stream for each layer up, just like peeling an onion layer by layer, which is the reason for calling it ONIONCODE. Here we introduce the concept of layer, where the receivers of the same layer have the same LED mixing state. And we assume that the 4 LEDs are non-uniformly distributed on a plane, which means that at the receiver side, 4 different mixing state can be observed, that is, 4 layers are generated. To summarize, ONIONCODE adopts a multi-priority broadcast transmission. Next, we explain the ONIONCODE transmission model in details. Assume that the sender needs to transmit 4-bit streams, corresponding to 4 priority layers. In a symbol period, we take 4 bits and compose the bits to be sent, named as DT. A specially designed encoding table maps DT to the LED's on/off state LT, which controls the LED array to light the corresponding lamp. Assuming that a layer 3 receiver observes the LED state as LR3, the brackets indicate that the corresponding LEDs have been mixed, that is, the receiver can observe one independent on LED, as well as a mix LED mixed by 3 LEDs and 2 of them are lit. Finally, the decoding table of layer 3 decodes LR3, keeping the high priority bits and discarding the low priority bits, where the bits indicated by X are discarded. The encoding and decoding tables are the core design of ONIONCODE. Next we briefly introduce the process of coding table generation. The key insight of ONIONCODE is that the remote camera cannot determine which LED in the array is turned on due to the severe mixing. But the camera can determine how many of them are lit by calculating the luminance value of the pixels. Keeping the key insight in mind, we first model the LED states that can be observed by each layer's receiver, and this is the foundation of the following derivation. As mentioned before, a layer 4 receiver can observe a mixed LED, mixed by 4 LEDs. This mixed LED has 5 states, with the number of on LED varying from 0 to 4. And a state contains a number of indistinguishable substates. For example, there are a total of 6 substates when 2 LEDs are lit. The substates of each state of layer 4 are 1, 4, 6, 4, 1. And the distribution of the substates is the key to the derivation of the coding table. The derivation of the codec table starts from the highest layer, that is layer 4. The bits to be decoded by layer 4 are 0xxx and 1xxx. The 3 x's need to accommodate 8 possible 0-1 combinations, so we map these 2 states to 0xxx and these 3 to 1xxx. Then, we focus on the 8 substates mapped to 0xxx. These 8 substates are redistributed in layer 3. In layer 3, we need to assign 00xx and 01xx. 2x here means 4 uncertain states. Hence, these 4 substates are mapped to 00XX, and these 4 for 01XX. This process can be carried out to layer 2 and layer 1. Obviously, the above process is recursive and symmetric. From layer 4 to layer 1, we get the mapping of LED states to decoded bits for each layer, that is, the decoding tables of each layer. By reversing the decoding table of layer 1, we can get the encoding table of the transmitter. Here is an example. Assuming that the sender needs to send data bits 1100, the encoding table tells us the LED on/off states should be 1001. The observed LED states of the receivers at layer 2 to 4 are here, with mixing state becoming severe. Using the decoding table of corresponding layer, the decoded data bits can be obtained, with the data rate becoming smaller, because more bit streams are discarded. In the paper, we show that this coding approach holds for any number of LEDs. We establish an proof-of-concept OCC system enhanced by the proposed ONIONCODE and a carefully designed frame structure to ensure successful decoding at the receiver. The sender first encodes the multi-priority bit stream using the encoding table to get the payload. Then, a specific preamble is added, consisting of 3 sub-preamble. The receiver captures consecutive video frames and first performs time synchronization and fine-grained LED segmentation based on sub-preamble 1, helping the receiver to determine the current layer. Then, the sub-preamble 2 helps the receiver to adjust the camera exposure parameters to maximize the SNR. Then, sub-preamble 3 lights up each LED in turn to complete the channel estimation at the receiver with as little overhead as possible. Finally, the decoding of each LED channel is performed according to the threshold, and use the specific decoding table to decode. In evaluation, we implement an ONIONCODE prototype, using commercial off-the-shelf digital camera and LED array. For the sender, the LED array is controlled by a programmable controller and powered by a switching power supply. For the receiver, we test 3 types of commonly used cameras including SLR camera, drone-mounted camera and mobile phones camera. The receivers are placed at 10 to 40 meters from the sender to test the performance of ONIONCODE. We have conducted rich experiments to evaluate the communication performance of ONIONCODE prototype, including preamble detection rate under various environment factors, performance of the proposed adaptive camera configuration and channel estimation, robustness under various hardware and environment factors. We compare ONIONCODE with the state-of-the-art hierarchical coding scheme, overlay coding, under a 4-layer design. The results show a 67% increase in the overall normalized throughput. The audience can read our paper to get more detailed information on your interested evaluation results. In conclusion, we design a novel hierarchical coding that enables multi-priority transmission in optical camera communication, named as ONIONCODE. ONIONCODE is a non-block-based hierarchical coding scheme that avoids data rate loss of near receivers, allowing multi-receiver to dynamically discard low-priority data according to the measured optical channel states and reserve the highest priority data. Experiment shows that ONIONCODE has a 67% increase in overall throughput compared with the state-of-the-art coding scheme. And we implement an OCC prototype enhanced by ONIONCODE, using commercial off-the-shelf LED array and cameras. A series of communication mechanisms are designed to ensure synchronization and decoding at the receiver. The above all is our video. Thanks for watching.